Welcome to the condensed cryptographic currency crash course. My name is Aljoscha Jutmeier. I'm a PhD student at the Technical University of Vienna, and I'm also working at SBA Research, and I will guide you through this tutorial. If you're looking at the title, you may ask why this lengthy title. When we, me myself and together with my advisor Edgar Weipel, prepared this tutorial, it was actually called just Cryptographic Currency Crash Course, so C4, but we had to fit it into a smaller time slot, and therefore we had to shorten it a little, and that's why the condensed is here. That's also why I'm standing here alone presenting it. First of all, I want to start with some organizational remarks. You're probably interested in the slides. You can just find the slides online here. This is the QR code if you want to use your smartphone and make a photo. On the slides, I have a lot of references to literature. For example, they are written like this, Nakamoto 2008 Bitcoin. If you see such a reference, it points to the bibliography of this tutorial, where I'm collecting basically literature related to Bitcoin and cryptographic currencies in general. You can find an HTML export of all the publications here on this URL. So every time you see such a reference, it's the name in this bibliography. If you're further interested, there is also a link on this page to even more references in the GitHub repository. I don't know if you have already read this in the preface, but there are also some challenges during this tutorial. So you can win small amounts of Bitcoin during this tutorial. Don't get overly excited, it's just really small amounts. We are not early adopters, so we are not hoarding large amounts of coins. How does this work? There are two ways in which you can earn fractions of a coin. The one is questions during the tutorial, where I ask you a question and you just raise your hand, and then I pick one of you. I try to be a fair scheduler. And the other one are challenges on this URL. To participate, you need to register at this URL, an account. There is no credentials or personal identifiable information required, just a nickname, a password, and some valid Bitcoin address, and this is important. To avoid Sybil attacks and to avoid that a lot of people register more than one account and solve the same challenges with more than one account, you need a token to register an account. And I would ask some of the helping hands here to hand out a token or one of these sheets of paper to everyone in the audience. And the right ones, yes. And with these tokens, you can register an account. Regarding the questions, every time you're correctly answering a question, you get one of these coupon codes, which you can then use on this website to claim that you have answered this question correctly. This will be handed out during the tutorial. Every time when I ask a question, you get one of those. You don't have to register now. I will leave up this page during the whole conference, the remaining conference, so you can just collect these and then later on, somewhere in a break, register an account and claim all of these and look at the challenges later on. So yeah, if you want to participate, the first challenge would be obviously to register, get a valid Bitcoin address. If you don't have a valid Bitcoin address or a wallet by now, here on this side you find some suggestions of wallets. If you want to force me into a recommendation, if you have an Android smartphone, my Cilium wallet is pretty good. So, a short preface on this topic. Who has already owned some forms of cryptographic currencies, Bitcoin or other cryptographic currencies? Okay, one, two, couple of, yeah. Actually, when I started to prepare the tutorial, I created a tag cloud over all publications since 2009 in the bibliography I showed you, to be sure to don't miss some important topics and terminologies. because I wanted to explain the, let's say, the important terminologies used in this kind of field. And when you usually prepare a tutorial or want to introduce somebody to a field, you look up the important terms, and maybe you start usually with some definitions, and then you go into further detail and give more explanations and so on. And it quickly turned out that this is not quite the right approach for this kind of field. And I want to show you why. Like, for example, take the term cryptographic currency. If you're looking for a definition of cryptographic currency, you came across the definition of a virtual currency, which is the only thing that is kind of well defined by the European Banking Authority, for example. And they say virtual currency is some issued is an issued currency controlled by its developers. So an example for a virtual currency would have been Amazon coins or World of Warcraft gold or something like that. So the important point here from the legal perspective is issued. But even that has changed. 2014, I guess, the European Banking Authority redefined this term, and now it's a digital representation of value that is neither issued by a central bank or a public authority. So under the first definition, Bitcoin and cryptographic currencies would not have been a virtual currency because it's not directly issued and it's not directly controlled by its developers. And according to the second definition, it might well be. So again, it's not really clear where it's located. So there's no universally agreed definition what really is a cryptographic currency. There are, of course, some definitions. What they have in common mostly is that they are all about decentralized control, and they also mention the term digital currency. When you're looking into another important term that is often used in this context, blockchain, and you're searching for a definition, you will also find that there is no universally agreed definition. There are a couple of definitions. I will give you two later on in this tutorial. But again, it looks like it's not that well defined. And even the funny thing is, even the spelling of blockchain is not well defined. So ignoring capital letters, you often find it blockchain with a space and blockchain as one term. So why is that? Cannot be that hard. Why is it? Let's look at the original publication of Satoshi Nakamoto. Look how he wrote blockchain. This would have been it, or this must be the correct way to do it. But if you're looking in the original publication and you're searching for blockchain, either with space or without space, you find 0 occurrences of this term. So in the original publication, word blockchain does not even occur. He was always talking about blocks and chains, but not the word blockchain by itself. So it was invented later on. You might also look into the source code. If you're looking into original source code, you find one mentioning of Satoshi Nakamoto of blockchain, and here he wrote it with a space. So you mean, okay, good, the right way to write it would be with a space. But as soon as you search different Wikipedias, you see again different writings. You see on the English Wikipedia, blockchain is one word, the German Wikipedia has a space, and also the Bitcoin Wiki has a space. Yeah, as a developer, if you don't know how to write something, you look at Stack Exchange, and here also it would have been written with, the recommendation would be with space. So looks like it should be written with space, but what does Google say? If you enter it with space, Google says, did you mean blockchain? So it looks like the current way to write it is with one word. And even if you're concerning the academic literature and grab over all the publications in the bibliography I showed you, you're seeing that it's most likely now blockchain as one word. And that's also why I go with this writing for the rest of this tutorial. So you see this field is kind of differently structured. So why are the characteristics of this field kind of different? And I pointed out 3 reasons why I think this might be the case. The first is very community-driven, and it's a very interdisciplinary topic, and of course it's a hype topic currently. What do I mean by community-driven? Community-driven, by community-driven I mean it lives from quick online publication and discussion. If you're looking at the original publication of Satoshi Nakamoto, 2009, it was not published on some scientific venue. It was basically just released in the open and together with the source code, and then it was there and the people started working on it, playing with the source code, developing it. That's also another interesting criteria or property of this field. It lives very much from rapid free software development. And also there's this strong distributed without trusted third party mindset, which might also relate to that there's a lack of clear definitions often. And also a lot of startup company and also scams are involved. Another aspect is that this field of cryptographic currencies is very interdisciplinary. So regarding cryptocurrencies, they attract a lot of different communities and actors. So you find technically interested people, you find ideologists, you find startups, large enterprises, public authorities, banks, financial regulators, businessmen, investors, criminals, and so on. So basically there are a lot of groups interested in this topic. And this topic has also a lot of different aspects. So you can look at various different directions on this topic. You can look from the economical side, you can look from the legal side, the sociological side, game theoretic side, usability side, technological side, and here you can differentiate between network and distributed systems aspects, cryptographic aspects, language security aspects when you're looking at smart contracts and so on. So it's a very broad topic. And of course, it's a hype topic. Since Bitcoin, about 700 cryptographic currencies have been created, and there's a lot of going on in this field. These are some of the headlines from, more or less respected news sites, and you see there are always increasing in superlatives. So blockchain, kann fast alles is German, which says can almost do everything. How blockchain technology can change the world. And if you think there cannot be a headline adding another superlative to this topic, there always comes a new one, like for example Guardian, which says blockchain, the answer to life, the universe, and everything. At least it was the question mark here. So it truly is a hype topic, and it's also heavily discussed in companies. I guess this situation might be familiar. Here the CEO comes in and said, I've hired a consultant to help involve our products use blockchain technology. And here's the consultant and she's saying blockchain, blockchain, blockchain. The CEO is clapping, yeah, it's if you're a technologist and a philosopher at the same time. So what's the goal of this tutorial? Above all, it's a crash course in cryptographic currency technologies, and we're looking at it solely from a technological point of view. And as a crash course, it should teach you a lot of basic facts in a very short time. The main idea is to present you the technologies, the underlying technologies that drive the field, and that you get a good understanding of Bitcoin and blockchain mechanics. Since when you remember the tech cloud, Bitcoin transactions and all these important topics were a very core point of this new field of distributed cryptographic currencies. If you already are familiar with cryptographic currencies, maybe there are some details you are getting from this tutorial, because I will try to poke into the details sometimes. Questions are welcome at any time. So if you want to raise a question, just raise your hands and I will try to answer it. Good. According to the agenda, we will first look into the history a little bit, then we will describe Bitcoin and a lot of important terminologies, which are then used in, I guess, almost any other publications after that. Then we will look at consensus in the context of blockchain or distributed blockchains or distributed cryptographic currencies, and differentiate between the types of blockchains that are now in the wild. So, history of cryptographic currencies. The field of cryptographic currencies actually dates back to the 80s. So, although there has not been any commercially successful, yes, there's a question? Pardon? The URL for the slides. Do you have received one of these? There should be a URL on these tokens, and if you are, if you're heading the challenge environment on port 8443, there should be the URL for the slides on this landing page. If you're going to this URL. Yeah, so actually the topic of cryptographic currencies dates back to the 80s. to David Chaum, who was the first one who basically brought up the idea of a cryptographic currency after he invented blind signatures. And interestingly, another publication of him, Security Without Identification, Transaction Systems to Make Big Brother Obsolete, is also claimed to be the roots of the cypherpunks movement, which were very active during the crypto wars. During the 90s, there was kind of a dry period regarding cryptographic currencies, but the crypto wars were going on, heavily fought, let's say it that way. For example, the cypherpunks mailing list was started. Then there was this whole discussion with the Clipper chip, which was basically a hardware backdoor for cryptography. And a lot of activism was going on. You will then see why I'm here explicitly referring to Evan Beck, because he later was also active in the cryptocurrency community. So this is basically where the idea originated. This was also some interesting example I find kind of funny. Adam Beck also wrote a version of RSA in 3 lines of Perl that was then later put on a t-shirt, because at that time strong cryptography was still considered as ammunition in the US, and therefore this t-shirt would not be exportable, and it was called the non-exportable t-shirt because it was basically ammunition. So then in the 19s there started the idea of B-money and Hashcash. These 2 publications here are kind of remarkable or outstanding because these are the only ones Satoshi Nakamoto actually referred to in his Bitcoin publication. So he does not refer to any other publications in the field of cryptographic currencies or distributed systems despite those 2. Hashcash and later on reusable proof of works was an interesting part or an important development when you're looking later at Bitcoin, because they're one of the main foundations of today's proof of work cryptographic currencies. How does a proof of work work? It requires a hash function, a cryptographically secure hash function. And for hash functions, you have a finite number of input bits, in this example 512, and you get a fixed number of output bits. For example, if you're using SHA-256, there are 256 output bits. So you have a large input set and an always fixed small output set. And if you're applying the hash function, you're mapping one message here to an output here. So do it again, get a different output. So every single change of one input bit here should result into a large change in the output, should result into a different value. Of course, since there are more input values possible than actually output values, there surely must be collisions. So if you have more input bits than output bits, there must be other messages that result to the same hash. Warm-up question: how many tries do you need to make to certainly find a collision when your hash function has 256 output bits? How often do you have to try to, in the worst case, to find a collision? How many tries are there?
2 to the 256 divided by 2.
The start was correct, yes?
2 to the 128?
No. Yeah. He was showing up hands first, yes?
I would say 2 to the power of 256 plus 1.
Exactly, you earned yourself some coins. So don't know if some of you wanna hand out the coins or every time someone answers a question correctly. Don't use up all the tokens in the meanwhile while you're sitting on your laptop back there. Okay, yeah, correctly. 2 to the power of 256 plus 1. Then you have exhausted all the output space, and therefore your next try certainly should yield a collision. Anybody an idea how many tries you need to have the probability of roughly 50% to reach a collision? After how many tries would you? Yes.
228.
2 what? 2 to the power of?
128.
Yes, exactly. you also earned yourself some coins. So this is called the bursty bound, and after 2 to 128 tries, you have a probability of 50% to reach a collision. So 2 to the power of 128 looks kind of impractical if you're stated in different terms. It would take 10 to the power of 27 years to calculate 2 to the power of 128 hashes. And there is also a nice quote in the Princeton Bitcoin book, which I'm citing very often during this tutorial. If you take every computer ever made by humanity and let them compute since the beginning of the entire universe until now, the odds that you will find a collision is still infinitely small, so small that it's less than the odds that the Earth will be destroyed by a giant meteor in the next 2 seconds. Yeah. Which didn't happen, luckily. So it's kind of impractical if you're searching for direct collisions. So what you want for proof of work is that it's easy to verify, difficult to compute, and you want the difficulty to be parameterizable. So how to achieve this? The solution is to create a hash or search puzzle which is based on a partial preimage attack. And this requires a secure hash function, some random value, a target set, and you're searching for a message M composed out of a random value, the value X, and this message hash should be an element of the target set. How does this look like? So for example, you're not requiring 1 collisions, you have a set of possible outputs that is considered valid. And if you're hashing a message and this is within this set, M is a valid solution of the puzzle. This will, of course, would not be a valid solution of the puzzle. How does this look in Bitcoin? In Bitcoin, the size of this set is defined by the required number of 0 bits in front of the resulting SHA-256 hash. And if you require a smaller number of leading 0 bits, then there, of course, are a large number of possible valid solutions, so the set is large. If you're requiring a lot of 0 bits, then the set of possible solutions gets smaller, so the proof of work is more difficult. And that's basically the idea of proof of work in Bitcoin. How was this actually introduced, or what was the original idea behind it in Hashcash? Hashcash actually used this as a kind of denial of service prevention techniques for email spam. So they required that every email relayed by their email server contains an additional email header that looks like this. And this header was composed with the following fields. And the important fields were the target, the recipient email address, and then there was a random value, and there was a nonce. And the task now, if you want to relay an email or send an email, was to find a nonce value that when this whole header line will be hashed with the use of SHA-1 sum, then this hash should begin with the required number of 0 bits, and only then the message will be relayed. So if you would have been a spammer, you would want to send a lot of messages to different email addresses. You would have to do this proof of work and these calculations for every message you want to send, and therefore it gets harder to send a lot of messages because you have to find a valid nonce for every message. Then Bitcoin came along. In 2008, the original Bitcoin publication was made, and later on, 2009, the Bitcoin network basically started, and Hal Finney became the first identified Bitcoin user because he was the one who first received the transaction by Satoshi Nakamoto in the beginning of 2009. Regarding the academic view of this, because Bitcoin was just released and then there was a community building around it, the first peer-reviewed publication regarding Bitcoin and this new age of cryptographic currencies was in 2011, and it was on an analysis of anonymity in the Bitcoin system. So it focused on the anonymity aspects, and since then the number of just the peer-reviewed publications rose and rose and rose, and you see clearly that now this, there is a large number. I don't know if for 2016 I have not even computed it now. So clearly there's a lot of interest in this topic. The original Bitcoin, or when Bitcoin started, Satoshi Nakamoto created the first block in the Bitcoin blockchain, which is also called the Genesis block. And he included in the first block the headline of the New York Times at that time, which was this from the 3rd January of 2009. And it states, "Chancellor on brink of second bailout of banks." Question, what does this inclusion of this string in the first block of the blockchain proves? If you're including the headline of the newspaper. I guess you were first?
That it was not published before that date.
Exactly. Exactly. Later on we will again remember this and talk about which attack this will prevent. So it ensures that that is not published before that date. Could have been created every time after, but not before this date. So some basic facts about Bitcoin. It's a currency symbol used by the community is BTC. There is also an official symbol, XBT. This is actually the slide I have to date up the most often because the exchange rate changes that fast. So currently it's about $650 US, and the all-time high was around at $1,125 US. The current market capitalization is about 10 billion, and there are already 60 million Bitcoins mined and available as available supply. Quick side remark, if you're from a different country and here in Austria and want to buy Bitcoins, in Austria it's actually quite easy to acquire Bitcoins because you can buy them at a lot of tobacco shops where I also can buy cigarettes and magazines. So if you're interested, I don't get any benefits from it. The company that is selling it is called Bitcoin Bon. Just if you want to use the chance and buy some Bitcoins, this is quite easy in Austria. So some short note on the supply of Bitcoins. You probably have heard that there is a limited supply of 21 million Bitcoins. Actually, first of all, actually 1 Bitcoin is not the smallest unit. It's divisible. Again, it has 8 decimal places, and the smallest unit actually is a Satoshi, and 1 Bitcoin is 10 to the power of 8 Satoshis. That's actually the smallest unit. And you probably have heard that there is a limited number of Bitcoins, but it's not. There's no real cryptographic limit on the number of Bitcoins. It's just by convention. So as long as most of the network is holding to this definition or to this definition or to this basically this agreement, there will be this finite amount of 21 million. How is this implemented? Basically, the reference implementation Bitcoin Core has a rule that every 200,010 blocks, the block reward you receive for mining a block is halved. So in the first era, there were 50 Bitcoins block reward, then half 50, then 25, and now we have 12.5. And in the last era, 33, the amount will have reached the smallest value, which is 1 Satoshi, and after this, there will be no block reward. So actually, it's basically a software limit that holds until everybody is using the same software, the software that is compliant to this kind of limit. And even with the current maximum number of Bitcoins, which is 20 million, that would be the equivalent of this amount of Satoshi. So there would be 2 quadrillion Satoshis. If you would compare this to the amount of US dollar in the world, the M2 money supply of the US dollar in the world is about 10 trillion. So there still are currently more Satoshis than US dollars, so it should not be a problem from that point of perspective. And even if you make a software change and the community agrees and everyone is adapting to it, it's still, if you're using the reserved field, which is a 64-bit integer, you would reach a theoretical maximum of 9 quintillion. So it's even with the data field that is reserved for now but not used, you can reach huge amounts of coins. So this should not be the problem. Then Bitcoin created, of course, this boom and hype in cryptographic currencies, with 700 cryptographic currencies around currently, most of which are somehow forks of the original Bitcoin implementation, but there are also some completely different designs. If you're interested in the history of Bitcoin and how all these forks develop, there is a nice site, Map of Coins, where we can show all the relations between different currencies. And I also have a question. Does some of you know which currency was the first fork of Bitcoin? Yes? Exactly, Namecoin was the first fork of Bitcoin. Interesting fun fact, the inventor of Namecoin kind of disappeared at approximately the same time as Satoshi Nakamoto. So Namecoin was the first fork of Bitcoin. Now, there are a few large ones you probably heard about. Bitcoin is still the largest one in terms of market capitalization. Then there's Ethereum, Ripple, Litecoin, Ethereum Classic, and so on. Bitcoin and the blockchain. So now we're going over some basic concepts and terminologies in this context and describe all these terms often used in the literature. And we'll start with a Bitcoin address. Actually, a Bitcoin address is nothing more than a hash of a public key. Does some of you know what's the hash function that is applied last to the public key to form a Bitcoin address before base 58 encoding? RIPE-MD, exactly. In detail, it's actually a little bit more sophisticated. There is this kind of identification bit. This is basically the elliptic curve digital signature other than public key. Then SHA-256 is applied, then RIPE-MD, and there also this green part is actually just a checksum at the end. And this all is base 58 encoded, and that's basically the Bitcoin address. So when you're having a Bitcoin address, you're basically holding a public key, and a hash of a public key. These are some of the version bits identifying either different address formats, or if there's a 5 at the beginning, it's a private key. You should never hand out those, but usually you don't get it not displayed easily in your client. Then there's testnet addresses and so on. So since Bitcoin addresses are private and public key pairs, it's actually possible to prove ownership of a Bitcoin address by signing a message with your private key and so thereby prove that you're in the possession of this Bitcoin address and the coins that are available on this address. We actually did that for a survey to prove that we are in possession of the promised rewards. So with that knowledge equipped, you have enough to receive Bitcoins without knowing anything about the protocol. So basically anybody can create a Bitcoin address because it's just a public-private key pair. The most easiest way to do so, depending on whether you trust the JavaScript implementation, is on bitcoinaddress.org, where you just fire up a browser, then the Bitcoin address is created completely in JavaScript, and then the private key and the public key part are displayed to you. So this is basically everything to use Bitcoin. But now we want to look at the protocol that's underneath it. So important concept of Bitcoins are blocks. What is a block? A block contains a header and transactions. It's important to differentiate between two notions. The one is transactions and the other one is blocks. So transactions can basically be created by anybody who owns currency units, and they're used to transfer those units. And blocks encapsulate the number of transactions and are created by miners, so they require the proof of work. And the blocks actually are the part that synchronizes this timeline and synchronizes the network. Both transactions and blocks are broadcasted or disseminated via a gossiping protocol to all nodes in the Bitcoin peer-to-peer network. But we'll leave this aside by now. How's a block formatted? A block header contains some version information, some timestamp. It contains a Merkle tree root hash of all transactions associated with this block. So basically, all transactions are linked to the block header via this Merkle tree root. It, of course, contains the hash of the previous block, and it contains some target and some nonce value. What's the target? The target basically is translated to the number of required 0 bits of the SHA-256 functions that is used for proving or creating a valid proof of work. And the nonce actually is the random field you can increment and change until you find a valid proof of work solution. How does this look like? Mining, or actually finding a proof of work, is basically hashing this block header. Then take a look if the resulting hash starts with the required number of 0 bits. If yes, the proof of work is valid. If no, it's invalid. So for example, if you take a non-zero, try it, hash this block header, then look at the output and say, okay, it does not start with 0 bits, with enough 0 bits because there's a 1 in it, then the solution is invalid. Try again, some different solution, again not the required number of zeros, is again invalid. Luckily, with nonce of 2, this results in a hash that starts with the required number of zeros, and this block would be valid, and you can submit it to the Bitcoin and peer-to-peer network, and it will eventually be included in one of the chains, in the Bitcoin blockchain. So this is basically what goes on during mining. Of course, after this has happened and this block gets included into the blockchain, the miners are switching to the next block, again collecting all the transactions that have not been included in a Bitcoin block so far, and again start the same game, start searching for a nonce, and try nonce values until they find a new block. So this is what goes on in mining, and here you have the hash of the previous block as a reference, which starts with the number of zeros shown you before. So basically this block, when this block is currently mined or the nonce is currently brute forced, all transactions that are not in a block that's already appended to the blockchain are called unconfirmed transactions or zero confirmation attacks. Transactions that are on the head of the blockchain, so are in the block that's already appended to the blockchain that has a valid proof of work, are confirmed transactions, and in this case, if they're in the head of the blockchain, they have one confirmation. We will look at this a little bit later on. I guess we quickly skip the mining and the difficulty target details. You can look it up in the slides if you want to, if you're deeply interested. Maybe just important thing is that the difficulty of the Bitcoin network is not constant. It's adjusted, and depending on how fast the last 2016 blocks have been created, and it's possible for the difficulty to actually go down again if miners drop out of the network, and it goes up again if miners join the network. So, where do Bitcoins come into existence? Actually, every first transaction in a block is a special transaction, which is called coin-based transactions. This coin-based transactions is special because it's the only transaction that has no inputs. Every transaction is composed out of version information, a counter of inputs, then the inputs to this transaction, some locking parameter where you can lock the transaction until some number or some block height in the Bitcoin blockchain, which is not that relevant right now, and an out counter which defines the number of outputs. And this coin-based transaction, which is the first transaction in every block, is kind of special because it has no inputs. The input field is basically, it just has one input, which is a Coinbase, and this input basically creates new Bitcoins out of thin air, and here currently that would be 12.5 Bitcoins. And these Bitcoins are transacted to the output address, and this is probably the output address of the miner who puts in his Bitcoin address, and if the block gets minted and the block gets appended to the blockchain, the miner would have a Coinbase transaction included, which basically creates 12.5 Bitcoins out of thin air and transacts them to his Bitcoin address. So he is richer by 12.5 Bitcoins. Yes, this of course all happens when the block is mined and appended to the chain. So since Bitcoin does not use any form of encryption, really, it does only uses signing, but not encryption and hashing. What if a Bitcoin address, a new block minted by a miner is transmitted over the network, and a man-in-the-middle attack occurs, and someone is trying to change this reward Bitcoin address of the miner to his Bitcoin address, for example, Mallory, which is the hash of the public key of Mallory. Why is that not possible? Yes, you were You were first, but you already have one. Yes, you?
So this Merkle tree hash presumably contains the hash of this transaction.
Yeah, I accept that. Yeah, basically that's the basic idea. So if the attacker would change the Bitcoin address, the output Bitcoin address to his, this would also change the Coinbase transaction, which in turn would also change the Merkle root, and this in turn would change the block header, which would change the hash of the block, and therefore the chances are good that the block header does not fulfill the proof of work requirements, and therefore the attacker would have to find a new valid nonce value, and if he can find new valid nonce values very fast, he is not required to even use man-in-the-middle attacks in the first place, because he can start mining by for his own and start participating legitimately in the Bitcoin network. So you see, Bitcoin also has a clever incentive engineering aspect. And this is also kind of new for a distributed cryptographic currency. So the means why Bitcoin works as a currency are not purely technical, but also by a clever incentive engineering. So you can also put it that way, that Bitcoin works as a currency only because it's a currency, which is kind of interesting. So how does transaction actually work? If Alice wants to transact some Bitcoins to Bob, she creates a transaction. The transaction again looks kind of same as the Coinbase. They have a version, inputs, and outputs. So since Alice wants to transfer coins to Bob, she adds Bob's Bitcoin address as an output address. And then she requires some inputs. So therefore, she has to search the blockchain for other outputs that were transferred to her Bitcoin addresses. This can be anywhere in the blockchain. In our example, we say it's just the head of the blockchain, basically the last block. So in the last block, there was a transaction containing multiple inputs and multiple outputs, where one of these outputs actually was to one of Alice's Bitcoin addresses. So she is in possession, she is the only one who is in possession of the according private key to this Bitcoin address, to this public key, and therefore she is the only one who can reference this output and prove that she is the legitimate owner of this Bitcoin address by making a signature with her private key over this whole transaction, and thereby proving that this transaction is basically signed by the legitimate owner of this Bitcoin address output, and therefore by the legitimate owner of the Bitcoin addresses that belong to this output. And with this signature, she basically redirects the values here to the Bitcoin address here, and Bob should receive these values. Then, of course, this is just the transaction that was created. Then you, of course, the transaction still has to be transferred to the Bitcoin network. So Alice is gossiping it into the Bitcoin peer-to-peer network, and the transaction eventually gets included into a new block. And as soon as a new block is minted, Bob has won confirmation, and the coins from Alice have been transferred to Bob. Actually, it's a little more complicated than that, because Bitcoin uses a scripting language to achieve these tasks. And it's not basically just signing, it's some form of non-Turing complete scripting language that contains no loops. And outputs are actually called script public keys, and inputs are called script signatures. How does this look like? Here's one of the simple examples for paying to a public key hash. So you have this is a previous output, and this is the input. And for evaluating the script, the previous output of where some coins have been transferred to Alice, is just appended with the new input script, and then this script gets evaluated by the miners who received this transaction. So basically, since it's stack-based language, the signature here at the beginning is pushed on the stack. Then the public key is pushed on the stack, Alice is providing. Then the opcode for duplication doubles the elements on the stack. Then the first element on the stack is hashed. Then again, the public key hash is put on the stack. Then there is an opcode for equal verify, which just checks if the topmost elements are equal, and at the end, the signature is checked. So, and if the result is true, then the transaction is valid, and the transaction will be included in the blockchain. So here again, you can view this in the more elaborate example. So this is how it actually looks like, but I will go over this a little faster. You can look it up in the slides. The only thing that is important I want to mention here is what if there are 5 Bitcoins transacted to Alice on this address, but Alice just wanted to pay 3 Bitcoins to Bob, but she just has this one transaction she can unlock. How does she do this? How does she get some change? Yes?
She gets change from putting a second output to come back to herself.
Exactly. She just puts in a second output that goes back to herself and transacts the Bitcoin again to herself, and then she can later on claim this output. That's exactly how it works. Anybody of you know how transaction fees work? Yes? Exactly. You also earned yourself some coins. So transaction fees are the method used by Bitcoin when there will be no block reward. But at this conference yesterday, we have heard a nice talk where they analyzed this from a game theoretic perspective and said that this incentive system might not work. But the theory behind it would have been that when Bitcoin reaches its last era and there will be no block reward, then the system should work by itself by rewarding miners with transaction fees. And a transaction fee is basically everything that is not claimed by output. So if this transaction would happen, then 5 Bitcoins would be transacted, 3 Bitcoins would be transacted to Bob, but 5 Bitcoins went in this transaction in the input, then 2 Bitcoins remain, and these 2 Bitcoins are basically added to the Coinbase transaction and therefore are transferred to the miner. So this is the idea behind transaction fees. How does this work in context of a blockchain? Here again we see the Genesis block, and blocks are appended as described before to the blockchain. And of course, it can happen that at one point in time, since the network is not perfectly synchronized, it can happen that 2 nodes in the network find nearly simultaneously a block and append different blocks to the current head of the chain. This is called the blockchain fork. And I guess it happens also a couple, I have the numbers not correctly, but it happens occasionally. And the resolution mechanism to resolve such kind of fork is basically just to wait. If you're waiting, then miners decide on which chain they want to support or which chain they're going to mine. And usually it's the case that in the reference client that you're mining on the block you receive first. So miners which will receive this block first will append this block, and miners which will receive this block first will append on this block, leaving some game theoretical aspects and selfish mining aside by now. And since one of the miners will find the next block, he will append again the chain. Since the probability of finding a block is exponentially distributed, this system should resolve itself, and one chain will get eventually larger, and this always the largest chain is so-called the main chain and the valid chain. And when I say largest here, it's not just the largest in terms of number of blocks, because it has also be the largest in terms of mining difficulty that went into the chain. Because if you're just concerning the length of the block, it would be easy to create a chain starting from the Genesis block with extremely low difficulty until now, which would then exceed the current chain. But of course, it would not include that large difficulty that the Bitcoin blockchain has now. So it's not basically it's not the largest chain, it's the heaviest chain that counts. All blocks that are not in the main chain are called stale blocks, sometimes incorrectly referred to as orphaned blocks, but the correct term for these blocks that not went into the chain and basically then therefore don't exist in the reality of Bitcoin are called stale blocks. Now I want to bring up the question again, from which attack does the inclusion of the New York Times headline protect in this context? So remember, the Genesis block includes the headline of the New York Times, and from which theoretical attack this protects this kind of mechanism in context of this blocks chain appending and stuff like that. Longest chain or most difficult chain wins. Any ideas? No, it's yes.
Maybe the original main crew started mining on a, say, 5 years back, and then the longest chain.
Exactly. So the attack this prevents is theoretically Satoshi, the original creator, could have been, since he knows what he will create, could have been starting mining in the 60s with some secret, high optimized mining hardware, and created back then a longest chain that is now even longer than the current chain. And if Bitcoin will be successful, he can now release his longest chain. This is kind of a theoretical attack, but it's also covered by this kind of mechanism. Yes. The transaction in the stale blocks, since they are not included in the chain, they're invalid. So in most cases, there will be some transaction will be the same, since if valid miners are mining them, but some transaction might be different because the miners might have a different view of the network. These transactions that are not in this block, that are just in this block, are then again in the pool of unconfirmed transactions and eventually get included into the next blocks. So,
but this means that sometimes I have I think I have a confirmed transaction, but it will later go stale.
Exactly. Good question. We will cover this in a second. But that's exactly a point, and that's a good point. Going back to this original theoretical attack where you could have started mining very early on, there actually are hard-coded blocks in the reference implementation Bitcoin Core. So if you're downloading Bitcoin and start synchronizing with the network, there are actually old blocks that are hard-coded in the network, so that should prevent you from someone showing you a completely different chain. Let's talk about double spending and how this works. In a central system where you have a bank, and a bank is basically handling the transaction and the clearance, double spending is kind of easily detectable. For a decentralized system, it's kind of hard. There are basically two ways to handle this situation. The one is detect and correct, for example, a prosecution, or to try to prevent it. And Bitcoin does the second one, and it's kind of trying it with at least with a high probability and make it highly unlikely that double spends are happening. What is a double spend? A double spend is basically an attempt of an attacker, here called Mallory, that tries to trick a merchant that he is actually paid, but at the same time tries to convince the rest of the network that this transaction has never happened. Therefore, he creates two conflicting transactions. One in which he pays the merchant, so he pays from Mallory to Alice, and one in which he pays the amount again to himself, so he pays from Mallory to Mallory again. And the attack is successful if Mallory is able to convince Alice that he has paid her, and the attack is not successful if this is not the case. So Mallory creates these two conflicting transactions. They're basically referring to the same output in the blockchain. So they cannot both be valid because the coins can just be spent once. So either this one is valid or either this one. In this example, I included also some view of the network. And I assume that Mallory has a pretty good picture of the network and knows which nodes belong to Alice. This is not necessarily required for a successful double spend, but it's kind of helpful. If you want to look in more detail into this, there is a nice publication by Miller where they analyze the topology of the network. So Mallory, since Mallory knows where Alice is located in the network, he sends the transaction right, or basically the legit transaction to Alice, and to the other nodes in the network, he sends the different transaction. Since nodes accept do not accept contradicting transaction, they will propagate kind of this way. Alice will spread out, of course, her transaction. Then there is a node that might receive both nearly simultaneously. For this node, it depends which one he will receive first. So this is kind of a race here. So this is kind of unclear, but the other nodes will receive here, the rest of which will receive the fraudulent transaction, and the above ones will receive the legit transaction. Here, in this case, they will both exchange contradicting transactions, and this will be ignored by the host. Now, suppose that this node up here is mining the next block, B1, and therefore this block will contain this transaction, and therefore the double spend basically failed. If you're supposing that this node here will mine the next block, then the double spend would have been successful if Alice already has handed out her goods or made a transaction transferring other cryptographic currency amounts or other amounts of fiat currency. So in this case, the double spend would have been successful. Of course, not a different node needs to mine the new block. This block could also have been mined by Mallory. What is important is that one of the red nodes mines the new block. So if you're ignoring this network picture by now, Mallory, of course, if Mallory has a large amount of hashing power, she basically is not required to publish any conflicting transaction until Mallory has the largest chain. Then basically Mallory can step in, overrule the current chain, and the double spend would have been successful. So since Mallory contains the longest or hardest has the longest or hardest chain. So if you have large amounts of hash power, you can do it basically like that. So what's the strategy against double spending? That's one reason to prevent double spending is that's why the common wisdom is to wait for at least 6 blocks, which is equivalent to kind of 60 minutes. Because then the probability that this will happen, this overruling will happen, is reduced very much. The other thing that merchants are doing is they try to detect it by having a lot of nodes in the network that are looking for contradicting transactions. So if you're looking at how to model this race between a benign and the fraudulent blockchain, so the benign blockchain by network and the fraudulent chain by Mallory, assuming that Mallory has large amounts of hash power, and we're ignoring block withholding attacks and selfish mining for a while, the original publications, or as well as the first publication that looked into double spending by Rosenfeld, model this as some kind of random walk. And here on this figure, you see the attacker's hash rate on the x-axis, and on the y-axis, you see the double spend attack success probability. And the different colors are the number of confirmation blocks the merchant waits. The dotted line is the calculation by Rosenfeld, and the solid line is by Satoshi. What you can clearly see is if the attacker has a 50% hash rate, basically the system collapses and he can do double spends with any number of confirmations. But if you're looking more back, if you're, for example, looking for 2 confirmation blocks, then the attacker with 20% hash rate would have been at approximately a 20% chance to do a double spend when the merchant is just waiting for 2 confirmation blocks. If the merchant is instead waiting for 24 confirmation blocks, then the attacker would require about 40% to have the same success probability for an attack. If you want to see the difference between Rosenfeld and Satoshi is more, yes?
So, doesn't this approach require that any honest miner who receives 2 different transactions is able to distinguish which is the good one and which is the bad one of those 2?
Actually, the miner are not able to distinguish between these because for them it's just 2 contradicting transactions.
They select one of them, and if they select
Exactly.
the bad one, then the bad one wins all the time.
Exactly.
Exactly,
but so usually the strategy is to accept just the first one, ignoring replaced by fee proposals right now. But usually the strategy is I just accept the first one, and every invalid transaction I receive, any contradictory transaction I receive is not accepted.
Assumes that the network is designed in a way that the probability of receiving good and bad ones is equally distributed, right?
Yeah. So from a merchant side of view and from a user side of view, your strategy to avoid such things is, of course, to wait for more transactions, because if you have more confirmation blocks, because the more you wait, the more sure you can become that the transaction you are waiting or depending on is not reverted. So That's basically the approach used here. But you see from this picture, and this is related to your question beforehand, that Bitcoin and Nakamoto consensus systems are probabilistic systems. So their insurance or guarantees increase over time and increase with the number of blocks. But of course, since they are probabilistic systems, there still might be the infinitely small probability that I'm now taking my mobile phone and start mining, and my mobile phone, even though it's really poor in calculating hashes, creates 100 blocks in a row, which is very unlikely, but since it's a probabilistic system, there might be the possibility. This is just on a logarithmic scale. So you see that the differences are more in the lower regions of success probability. So yeah, I actually already said that. So it's a probabilistic system, and in either model, the attack probability, the successful attack probability for double spend decreases exponentially with the number of confirmation blocks. Yes. Hash rate means the number of tries or SHA-256 computations you can do compared to all the other miners in the network. This is a pie chart of the hash rates or the mining capabilities of large mining pools. Here you see the large ones like Antpool have around 19, from 16%, 11%, and so they proportionately receive most block rewards proportionate to their mining capabilities, to their hash rate. Yes?
Is there a way to cancel a transaction before it's been done?
Currently not. There might be with replace by fee, but actually there is no way to cancel it. Once the transaction is out, you're basically out of control, and it's up to the miners whether or not they include it or not. There is a proposal for replace by fee, where you can, as long as the transaction has not been included in the block, replace the transaction when you add a higher fee and change the sequence number. But I'm not sure if this rolled out already. Yes?
So since there clearly is a few of these mining pools that are kind of dominant in the network, doesn't this mean that if for some reason the sort of a large portion of these mining pools was a little bit offline, that would actually enable one of these bigger mining pools left to mount?
Yes, exactly. It has already been the case that there have been denial of service attacks against mining pools. That's why mining pools are try to stay hidden in the network and try not to disclose which nodes in the network belong to them, because as soon as some other mining pools might notice, they might try to knock them out of the network. And even if they have large amounts of hash power, if they're not able to publish their blocks, they're kind of not present and cannot mine. So yeah, denial of service attacks against mining pools have happened, and this is a problem, let's say.
Yeah, so on top of that, I guess you can always adjust your confirmation rate based on that quota you see there, right? So if you see that there's a pool that has half of the hash rate power, you can assume he has the potential to actually make fake transactions. So that means you increase the number of transactions that you would require. Do you get a live feed of that or close to live feed?
Actually, this data is from blockchain.info, and it's dependent on whether or not the pools are adding some kind of signatures to their blocks. So this is basically a summary out of the blocks that have been mined, because a lot of pools are writing some strings in the blocks they mine, so that they can be identified to which pool they belong. But you kind of get a live feed because you get a block every 10 minutes, so you know if there are suddenly a row of blocks that are not belong to any pool, you might get suspicious. There was another point you mentioned. I forgot right now. Yeah, if one of the pools gets more than 50%, which happened with some altcoins, what they're able to do is they're able to double spend and change, basically are a gatekeeper for what transactions to put in and what transactions to leave out of blocks. Because if they basically want to perform a denial of service attack, they can just create empty blocks without any transactions. So, but what they cannot do is they cannot steal any coins, because the coins are locked with the public-private key pair of the owner, so they cannot steal coins of other owners. They can just basically perform denial of service attacks and double spending attacks, which is still a kind of a major attack. So regarding the hash rate in general of the overall network, this is quite impressive because it's currently by 2 exahashes per second. And basically now it's infeasible to start mining with a CPU or even a GPU, because a lot of mining is performed by ASIC miners, so specialized CPUs that are just designed for performing fast hash computations. And you see just for a scale that it's not really feasible to start now working with your CPUs or start working without a pool. This is also some kind of nice figure that depicts the current hash rate situation quite well. So at the beginning there was a CPU mining going on, then it went to GPU grids, then to FPGAs, and now ASIC, which is kind of pit mining when you compare it to the gold rush. So in our last part, we want to talk about consensus in the context of blockchain. And I also will give you some definitions of the term blockchain to equip you with some definitions to avoid such situations where, again, a Dilbert comic, the CEO comes in and says, I think we should build a blockchain. And the tech guy, does he understand what he said? Or is it something he saw in a trade magazine ad? And then he asked, what color do you want your blockchain? And the CEO says, I think mauve has the most RAM. It's also kind of funny. Actually, this document is from the 90s, and it was originally a SQL database. Right? So how is blockchain defined? Actually, there are multiple definitions. And that's why I don't want to stick to one specific definition here, and I want to outline 2 shorter ones. And we will quickly look at the history of modeling Bitcoin and how this is related to defining what a blockchain is. And at the end, we will differentiate between the 2 main types of what is currently referred to as blockchain. So the first definition is from the Princeton Bitcoin book. That's why I called it the Princeton definition. And according to this definition, a blockchain is a linked list that is built with hash pointers instead of pointers. So you have some data blob, then you hash this data blob and append the hash of this data blob to the next block, then do it again, hash this whole thing and append it to the next block, and so on. And if you're storing your head at a safe place, you would detect any manipulations, because some manipulation here would be reflected in the hash here, would be reflected in the hash here, and so on. And you can detect this if you have kept your head of this chain. So this construction is not really new. Basically, the concepts were there about 30 years ago. But what is still good related to this definition is that it's very simple. And it holds true for all types of blockchains independent of the used consensus system. On the minor side, this definition only accounts for this offline data structure and does not mention any kind of consensus system, which is also kind of not optimal. And it assumes that the head of this chain is kept safe somehow. If you're looking at consensus in the context of blockchain, the central question is how to preserve the order of blocks in a chain in a permissionless peer-to-peer system. This is the great challenge Bitcoin solved, and this is actually the thing why Bitcoin and this distributed consensus it introduced is a new thing and a novelty, because this concept was not known before. And as you've seen, this is a probabilistic concept. It's not the case that every node in the network always has to agree on a total ordering of transactions and blocks, but at least for a common prefix of the chain, because there's still at the end of the chain, there might be some uncertainty, there might be forks, but for a common prefix of the chain, all of the nodes have to agree. There's also an interesting quote again from the Princeton Bitcoin book that says, ironically, with the current state of research, consensus in Bitcoin works better in practice than in theory. That is, we observe consensus working but have not developed the theory to fully explain why it works. This is kind of true, and this is still kind of true, although this was written in 2015. But it's still kind of true because there are still kind of gray areas in modeling Bitcoin and fully explain why this consensus system works and how it works. If you start looking into why this works, you have to look into the history of distributed systems and consensus systems, and this dates back to, again, to the 80s, to the Byzantine generals problem defined by Leslie Lamport here in a dedicated publication. It has been around before, but this is the dedicated publication of it. And there it defines the Byzantine generals problem. And this problem is kind of related to the question how to preserve the orders in the chain, because if you can solve, even if you can solve in a hostile network with Byzantine binary agreements, so if you can even agree on one bit, can have a consensus on one bit, you can agree on almost everything, whether it's blocks and transactions or something completely different. Short recap, what's the Byzantine generals problem? It's n generals that want to agree on a common battle plan. They're located around the city, and they want to agree on whether to attack or retreat. And f of these generals are malicious and are traitors and want to hinder an agreement or reach a state where some of the honest generals attack and some of the honest generals retreat, and then of course the attack would fail. Assuming a synchronous and reliable communication network between those generals, a solution would take n generals, or the total number of generals that is greater or equal 3 times the malicious generals plus 1. Of course, leaving other models and slight deviations aside, where you have authenticated messages and oral messages, this is the general unrestricted number required for a solution. Why it's not possible to do it with n equals 3 times the number of malicious generals? If you, for example, take n equals 3, so there are 3 generals, one of which is malicious. Depending on which one, there is one leader. It's the strategy for the malicious one to hinder an agreement would be to simply send contradicting orders to the other generals. So to one send attack, to the other one retreat. So every honest general receives one attack and one retreat order and therefore cannot agree on any strategy. So it requires 3f plus 1. Then, again in the 80s, there have been an impossibility proof regarding the Byzantine generals problem. This is the so-called famous Fisher-Lynch-Patterson proof. And my question now, if you know it, under which model does the FLP result proves that Byzantine generals or even consensus with one faulty node is not possible?
I think it was asynchronous without signatures.
Yes, without asynchronous, without signatures, and one word I'm missing here is which? Deterministic. Yeah, you both receive some. It proves that in an asynchronous communication model is that deterministic consensus cannot tolerate any failures at all. The basic idea of the proof is in an asynchronous communication network, you're not knowing when you send a message and you're waiting for a response, you do not know if the other side has crashed or if you still have not waited enough time. And that's why it's basically not possible, just in a small sketch. So this has been the impossibility result of Fisher-Lynch-Patterson. And luckily, in the 80s, there are also 2 remarkable publications, one by Ben Orr, one by Rabin. And the first one is another advantage of free choice, completely asynchronous agreement protocols, which basically introduced the concept of randomized consensus protocols. And again, Rabin showed this, that a randomized consensus protocol can be used to reach Byzantine agreement. This first one by Ben Orr was only considering crash fault, but in Byzantine agreement, you also consider malicious behavior of nodes. Side fact, these 2 publications, I guess it was last year, received the Dijkstra Prize for starting this field of randomized consensus. Then again, a dry period in the 90s, and in the end of the 19s, there's kind of this field revived, this consensus research with the work Practical Byzantine Fault Tolerance, which showed that you can reach that you can have a practical Byzantine fault tolerance system, which is still a deterministic one. It's called PPFD. This is currently used still in or in modified version in some cryptographic currencies like Ripple and Stellar are using this, or Hyperledger, I guess also. And this kind of revived this field again. Then there was some publication on Sybil attacks, some interesting survey about randomized consensus protocols, and what is also kind of interesting, Nick Szabo, the only one who also published, let's say, articles in the cryptocurrency community, also has some article on advancement in distributed security. So basically he brought this knowledge to the cryptocurrency community, I guess. Sorry. Then Bitcoin came along, and it basically just proposed this probabilistic system. And there's also an interesting quote from a survey paper. How does it solve the Byzantine-Generous problem? And they say, we can say Bitcoin tackles the Byzantine-Generous problem from a practical angle. How does this work, or how is the model of Bitcoin different? First, it surely is not a deterministic protocol. So that's also why this impossibility result of Fischer-Lynch-Patterson does not apply directly here. So it's surely a randomized or probabilistic, or sometimes called stabilizing consensus protocol. That's the first main difference. The other difference is that it uses a network of unknown size, so it does not know how many nodes are participating in mining, and which is equivalent to how many nodes are participating in consensus. So that's also sometimes stated that it supports anonymity. In the consensus language, they always use the term anonymity, although Bitcoin, strictly speaking, is not an anonymous system, but a pseudonymous system. As soon as you know the identity or the entity behind some Bitcoin address, you can follow the transactions of this entity. This second point here actually makes the problem much harder, because all of the previous systems required some unique IDs of nodes under which consensus should be reached, or some public keys. Therefore, this is why Bitcoin and proof-of-work based blockchains are called permissionless. The other thing is that it relies on at least some form of synchrony. I don't want to go in further detail into that, but Bitcoin actually bounds the delay after which messages we receive somehow. And what is also kind of a novel aspect, it introduces the idea of incentives, which is also kind of new for a consensus system. I already talked to you a little bit about that. It's that this idea of incentives is kind of new, and that's not that much important from a modeling and theoretical perspective, because this is hard to model and has not been done so far extensively, but it's very important from a practical perspective, because it motivates people to join the network and to start mining and to participate in the consensus. How is the consensus of Bitcoin informally described? Basically, it's like all transactions are broadcasted in the networks among all nodes under which consensus should be reached. And each node, each miner, collects the transactions into a block. And then every round, where round is equivalent to every new block, a random node in the network gets selected. This is done by the proof of work. And this random node is the leader for one round, so he's allowed to propose the next block. In the next round, another node does the exactly same thing, is selected, and then he is allowed to propose the next block. And now he's the leader, and he can decide whether or not to agree on the block before by appending on this block that has been created by the leader of the last round, or whether not append on this block and append on one block before that. So it's an implicit consensus mechanism where the leaders of every round agree to everything before by appending on it or by not appending on it. From the theory side, early modeling attempts showed, which have been done by Miller and Garay, showed that Bitcoin or proof-of-work blockchains in general can reach agreement where n is greater or equal to number of faulty or malicious nodes plus 1, which kind of would reflect the early analysis of this 50% attack. Although it's very important to state that this does not take into account new types of attacks like block withholding attacks and selfish mining attacks and special form of Sphinx attacks. But if you're interested in those, I can recommend you the tutorial today, one of the next tutorials today, where they will go into more detail and simulate those kinds of attacks. So the common wisdom and common recommendation is it should work very fine as long as the attacker has a hash rate not larger than 25%. Looking again at the timeline, the milestones are some interesting points in modeling. The first attempt, or the first further specification of the original approximations in the original Bitcoin publication, where there was no model introduced and only approximations, has been done by Rosenfeld in analysis of hash-based double spending. And he also he does not provide any model, but he further specified the original approximations. Then Miller was the first who started the attempt of modeling Bitcoin. Also an interesting publication in this field is the Bitcoin Backbone Protocol Analysis and Applications. In parallel to the attempts of modeling Bitcoin, I want to point out two publications that also were improving the attacks on Bitcoin. The one is by Eyal, who introduced block withholding attacks, also known as selfish mining. And this one combines this with eclipse attacks, so with the possibility to kind of isolate some nodes in the network to let them work for your chain. Sorry. And there are still, these are two not yet published on scientific venues papers, just preprints. Just wanted to point out that they're still, the model is still revisited and it's still ongoing to further specify it. I still owe you a definition of blockchain, and I wanted to give you a very recent one. And it's from this paper, which is only available as a preprint. It's from Pass, Simon and Schellert. And the definition is: a blockchain is an interactive protocol where each participant has a logical variable state, which contains a list of messages M called the chain. Players receive inputs called record patches or messages that they attempt to include in the chain of themselves and others. So with this definition, you clearly see that it's a protocol and that some form of consensus has to be reached. They also state some requirements that they should hold for a blockchain, which is consistency, self-consistency, mu chain quality, and G-chain growth. I just want to point out, due to lack of time, I just want to go into detail on the first two. Consistency basically states that with overwhelming probability in T, which is the number of blocks at the end of the chain, any point in the chain of two honest players can differ in only at least T blocks. This is the head of the chain, and so they should. This is the end of the chain, and they should only two blockchains of two honest players should only differ in the last T blocks of the chain. Everything before that should be agreed upon, but the last T blocks may differ. This is to account for this probabilistic aspect. And to avoid that, with the first definition, two honest nodes are swapping between chains. So with only the first definition, it would be valid to have a blockchain at the same blockchain with another node at all even blocks, and a completely different blockchain on all odd blocks with the same node. So it might be possible to switch blockchains on every new block. And therefore, future self-consistency is required to kind of fix the old blocks in the chain. Yeah, the advantage of this definition is that it clearly includes distributed systems aspect. On the downside, it's very specifically for proof-of-work blockchains. What's even a proof-of-work blockchain? What are there different ones? These are the two main types of blockchains. Proof-of-work blockchains, or when people say the word blockchain, they probably mean one of those. Proof-of-work blockchains, which are kind of like Bitcoin, Litecoin, Ethereum, Dogecoin, or something like that. And they all require proof of work and are somehow related to the Nakamoto consensus I described earlier. They're also sometimes called permissionless. And there are also Byzantine fault-tolerant blockchains, which are called sometimes permissioned or blockchains or consensus ledgers, and they use some other form of Byzantine fault-tolerance agreement system, like, for example, PPFT, like used in Ripple, Stellar, or Hyperledger. So if you compare those systems, which has been done by Vulkovic, you find some interesting differences in their characteristics. So on the one side, the proof of work are open, and the other ones are permissioned. So here you have to agree on a set of nodes under which consensus has to be reached. So you have to know the IDs of the nodes. Therefore, they're mostly deterministic and therefore have consensus finality because they have a number of rounds after which they surely agree and therefore have reached consensus. Whereas in a probabilistic system, the probability for reaching consensus just decreases. Last question regarding the scalability in number of nodes under which consensus has to be reached. Here the scalability is excellent. And I wanted to ask you why the number of nodes under which consensus has to be reached is excellent for proof of work blockchains. Why is it very performant to have a lot of, or is it basically very easy to add additional nodes and additional miners to Bitcoin? Whether here it might be somehow limited because here if you want to increase the number of nodes under which consensus should have been reached, the number of messages increases also. Yes?
On this node, any node can just start mining, and if you do the proof of work, you're a miner.
Exactly. Any node can just start mining, and no messages are produced, basically. You just need to fetch the current head of the chain, and you can start mining without producing any messages until you find a block. And here, in this setting, you have to, every new node adds another bunch of messages that has to be exchanged to include him into the consensus process. For the number of clients, so basically if you're just doing transactions, it's kind of the same in both types. If you're looking at performance, of course, here Bitcoin has kind of a low throughput. It's currently said that Bitcoin reaches 7 to 10 transactions per second compared to PayPal, which reaches a few hundred, or Visa, which reaches a few thousand. This is kind of low. This would be better in Byzantine fault-tolerant blockchains. And also the latency is kind of high in a probabilistic system because you have to wait for the number of confirmation blocks to be confident that your transaction has been included. Power consumption also is an issue for proof of work blockchains, and the tolerated power of the adversary is here mostly 33%, and here depending on what you're looking at on the modeling, it might be between 25 and 33. And yes?
How is this problem that you have to wait for confirmation done in practice? If I want to pay ice cream, do I then have to wait 5 hours?
In practice, there are payment providers that step in and take the risk. So if you want instant confirmation, you probably, as a merchant, use some payment provider like BitPay or something like that. And there are the people paid to BitPay. BitPay is then taking a fee, and they ensure you that you will get the money. So basically, they are taking the risk and collecting a fee to cover the expenses if there is a double spend and if this payment does not get confirmed. Yes?
I have one question about the scalability. So what I wonder is you have to store this blockchain, and the blockchain length grows with this number of transactions, which is depends probably on the number of clients. So is it really scalable in the number of clients?
Good point. How does the blockchain scale? To the lack of time, I suggest we talk later on. If you're also interested in this question, I just want to finish the conclusion. And if you have further questions, just catch me after the talk. So to conclude, we've heard a lot of, I've tried to explain a lot of terms because this is relevant if you want to read up on this topic. They are kind of used as a baseline in all further publications. We've shortly looked at the different types of blockchains. And of course, I demonstrated that Bitcoin led to increased interest again in this field of research, and there are still a lot of open challenges. If you want a good starting point for reading up on this, I can recommend these two systematization of knowledge papers and the Princeton Bitcoin book, and of course, everything on this bibliography. Thanks for your attention, and further questions to the lack of time. You have to go directly to me and ask me. Sorry.